All right, today we're jumping into the science of what I'd call an almost impossible weld. We're going to dive deep into the incredible physics and the super high-speed digital control that it takes to tame one of the most notoriously difficult materials out there, aluminum.
On paper, aluminum seems like the perfect material. It's super light, it's strong, but the second you try to weld it, it fights back. It creates a whole host of problems. So today, we're going to break down exactly how engineers finally figured out how to tame this thing. So, to really get this, we've got to understand the enemy here. Welding aluminum is nothing like welding steel. No way. It is a completely different beast, and it presents these unique challenges that have really pushed welding technology to its absolute limits.
And all of these problems are connected. First off, aluminum's got this tough, invisible oxide layer on the outside. That layer melts at a much, much higher temperature than the actual metal inside. Think of it like trying to melt an ice cube that's trapped inside a ceramic box. The metal also just sucks heat away like a sponge, which causes it to warp and distort all over the place. And on top of all that, it loves to trap gas bubbles and then crack apart as it cools down. It's a real mess.
Okay, so let's zoom in on that first big headache, porosity. Just imagine these tiny little pockets of air or gas trapped inside the solid metal. These bubbles, which are usually hydrogen from any tiny bit of moisture, dissolve right into the molten aluminum. But because the weld cools down so fast, that gas can't escape in time, and you're left with these little voids that can seriously weaken the whole joint.
And then you've got the other big villain, hot cracking. This happens at the absolute most vulnerable moment, when the weld is cooling down, but it's still kind of slushy, not quite solid. The metal is shrinking, and that creates stress. And if that stress pulls apart the delicate, crystallizing structure before it's fully solid, bam! You get these catastrophic cracks running right through your beautiful new weld.
So, you've got this material that's hard to melt cleanly, warps like crazy, traps gas, and cracks under pressure. How do you deal with it? Well, the answer isn't just more power. It's control. We're talking immense, precise, millisecond by millisecond control over the energy you're putting into the metal. And all of that comes down to controlling the electrical current. For the longest time, arc welding was basically just that, a fire hose of energy, a constant, high-power stream of electricity. Now, that's fine for simple stuff like steel, but for aluminum, it's total overkill. It just dumps way too much heat in, way too quickly, which makes all those problems, distortion, porosity, cracking, so much worse.
This is the idea that just changed everything. Instead of one constant blast of energy, what if you could pulse it? What if you could deliver just enough heat to get the metal melted and then immediately back off to let it cool just a little bit, all within a fraction of a second? This idea, pulsing the current, was the first massive breakthrough in getting real control.
And that, right there, leads us to the first major innovation we're going to talk about, pulsed arc welding. By breaking up that continuous stream of energy, engineers found they could manage heat in a way that was, well, previously impossible. And it directly tackled those core challenges of welding aluminum.
Now, this is not a simple on-off switch. Oh no. This is a complex, highly engineered signal. In a process like TIG welding, for example, engineers can control everything: the peak current, the background current, the frequency, even the polarity of the electricity. Every single part of this pulse is designed to do a specific job, giving the welder an absolutely incredible level of control.
And this crucial two-step dance is really the key. You have the peak current, that's the high-energy blast that does the heavy lifting, melting the aluminum and creating the weld pool. But then it immediately drops to a base current, which is just enough energy to keep the arc going, but it allows that molten pool to cool down and start to solidify before the next pulse hits. It's a brilliant rhythm.
So you can actually see what's happening physically here. During that peak current, the intense energy literally pushes the molten metal aside, creating what's called a keyhole that gives you deep penetration into the joint. Then, during that low current base phase, the pressure lets up and the molten metal flows right back in to fill the hole. This active management of the molten pool creates a weld that is so much stronger and more consistent. And this gets us right back to that pesky porosity problem. In GMAW or MIG welding, this pulsing action basically acts like a tiny stir for the molten weld pool. It agitates everything, and that agitation helps those trapped hydrogen bubbles work their way out and escape before the metal solidifies around them. It's such an elegant solution to a really persistent problem.
Pulsing was incredible,
A total game changer. But, engineers, they're never satisfied. They started asking, can we reduce the heat input even more? Can we make the process so controlled that it's fundamentally cold? And that pursuit, that question, led to the next major evolution in arc welding.
See, even with all the advanced pulsing, there was still this one little physics problem they couldn't quite crack. In MIG welding, you've got a wire that's continuously feeding into the arc. To get a droplet of molten metal to actually detach from the end of that wire, you usually need one final surge of current to kind of pinch it off. And that little surge, it adds extra unwanted heat. And that led to this brilliant question, the genius idea behind the next technology. Instead of relying on a final blast of electrical energy to break that droplet free, what if you could do it with motion? What if you could physically pull the wire back at the exact right millisecond to deposit one single perfect droplet with almost no extra energy at all? And that is cold metal transfer, or CMT. It's a completely revolutionary idea. A high-speed, digitally controlled wire feeder doesn't just push the wire forward, it actually yanks it backward. This physical retraction is what detaches the droplet, making the transfer of metal almost completely independent of the electrical force. It's wild. And the cycle itself is just beautiful in its simplicity. 1. The wire moves forward and touches the weld pool. 2. The machine's brain instantly detects that short circuit. 3. The current is immediately cut to almost zero. And 4. The wire feeder physically pulls back, snapping off one single droplet. And this whole cycle happens up to 70 times every single second. If you look at the waveform for CMT, you can see these moments where the current just plummets to nearly nothing. That's the magic. That's the mechanical retraction phase. Because there's no final energy surge to detach the droplet, the heat input is incredibly low. It's kind of like creating a seam by laying down a perfect series of tiny overlapping spot welds.
So what does all this high-speed digital control, from these complex pulse shapes to mechanical wire retraction, what does it actually get you in the real world? Well, the results are, honestly, they're transformative, especially for a tricky material like aluminum.
The benefits are just huge. I mean, with drastically lower heat, you get way less distortion and warping. You can now weld incredibly thin sheets of aluminum without just burning a hole right through them. And because the process is so gentle, you can even do things that were once considered impossible, like joining aluminum directly to steel. And on top of all of that, it's great at bridging gaps between parts, which is a massive advantage in any real-world fabrication shop.
And this chart really highlights a key practical advantage. Look, laser welding is the king of precision, right? But its tolerance for any kind of error is tiny. If your parts aren't perfectly aligned, you're in trouble. These advanced arc processes, like TIG and MIG, are way more forgiving of slight misalignments or gaps, which makes them incredibly robust and versatile out on the factory floor.
When you step back and look at it, this entire journey of innovation has taken us from a brute force, chaotic, almost uncontrollable arc to a process so refined and so precise that it can control a single drop of molten metal using digital logic and mechanical motion. It is just an incredible feat of engineering.
And that leaves us with a really fascinating thought. This story isn't just about welding. It's about achieving near-perfect control over energy and matter at a tiny scale. So as this technology keeps evolving, what other impossible materials are we going to be able to join and shape and build with? The possibilities are really, really exciting. Thanks for joining us.